Good morning to all. I am Dr.B.Angelin, Assistant Professor, Department of Information Technology, working in Dr. S.N.S. Rajalakshmi College of Arts and Science. Now I am going to discuss about operating system deadlocks. Deadlock and starvation. Deadlock is a scenario in operating system where two or more processors are unable to proceed because each process is waiting for a resource that is being held by another process. This situation creates a standstill where no progress can be made until the data deadline. This diagram shows the resource 1 and resource 2. We have two resources. Here we have a two process, the process 1 and process 2. Internal and design principles. When two trains approach each other at a crossing, both shall come to a full stop and neither shall start up again until other has gone. Statute passed by the Kansas State Legislature. Early in the 20th century, a treasury of railroad folklore B.A. Botkin and Alvin F. Harlow. This chapter continues our survey of concurrency by looking at two problems that plague all efforts to support concurrent processing: deadlock and starvation. We begin with a discussion of the underlying principles of deadlock and the related problems of starvation. Then we examine the three common approaches to dealing with deadlock. First one is prevention, then second one is deduction and avoidance. We then look at one of the classic problems used to illustrate both synchronization and deadlock issues, the dining philosopher's problem. Deadlock. The permanent blocking of a set of processes that either compete for system resources or communicate with each other. A set of processes is deadlocked when each process in the set is blocked awaiting an event that can only be triggered by another blocked process in the set. Permanent, no efficient solution. Deadlock can be defined as the permanent blocking of a set of processes that either compete for system resources or communicate with each other. A set of processors is deadlocked when each process in the set is blocked awaiting an event that can only be triggered by another blocked processes in the set. Deadlock is permanent because none of the events is ever triggered. Unlike other problems in concurrent process management, there is no efficient solution in general case. Potential deadlock. I need quad A and B. Animated slide click 1. Cars approach intersection. Then cars announce their resources needs. All deadlocks involve conflicting needs for resource by two or more processes. A common example is the traffic deadlock. Before the figure 6.1a shows a situation in which four cars have arrived at a four-way stop intersection at approximately the same time. The four quadrants of the intersections are the resources over which control is needed. The potential deadlock example: the car 1 traveling north needs a quadrants A and B. Car 2 needs a quadrant B and C. Car 3 needs a quadrant C and D. Car 4 needs quadrants D and A. The typical rule of the road in the United States is that a car at four-way stop should defer to a car immediately to its right. Actual deadlock: halt until D is free, halt until C is free. Halt until B is a free. Animated slide click 1. Cars move to deadlock. Then cars announce their resource need. However, if all four cars ignores the rules and proceed into the intersections at the same time, then each car seizes one resources but cannot proceed because the required second resources has already been seized by another car. This is an actual deadlock. Halt until A is free. Deadlock unpredictable. In the previous example we see, and like race condition, a set of processes deadlock when each process is the set is blocked awaiting an event. Deadlock is permanent because none of the events is ever triggered. Unlike other problems is concurrent process management. There is no efficient solution in the general case. Thank you.